MCA data is the raw XRF fluorescence spectrum recorded for every pixel. In this video, we're going to go over how you're going to process and import that data into SMAC so that you can use it for deeper interrogation of your map data. MCA data is actually being recorded during your experimental run, but it's quite large and stored on a separate server. We have to compress it and then copy it over your T drive after your experimental run is finished. So when you look in your T drive, as we have in the example of mine here, we have our XRF and XAS folders, but we also have a tar.gz file. This is the zipped MCA data, and usually has your surname followed by the month and year of your experiment. The first thing we need to do is to uncompress this zip file. Windows and Mac do this in slightly different ways. Macs tend to automatically open up this initial zip file and then show you a list of the individual zip files. Windows, on the other hand, you need an app like 7-zip or something similar and go through the process of uncompressing it. This can take a little while, so I've already gone ahead and uncompressed this zip file. It usually creates a folder called temp1, temp, zip temp1, or something of that nature, depending on how old your data is. But once you've expanded that main file, you then see in this directory a series of other tar.gz files separated into your individual maps. If you then go and unzip one of these files, the map that you're interested in, it will then create another directory, again zip temp or something similar. And inside there, you should have a whole series of HDF5 map files. You'll have an HDF5 file for every single line of the map you collected. So in this case, this map was 623 lines tall, so there are 623 HDF5 files. Once we've done that, we then need to do a couple of things within SMAC so that SMAC can see this data as one solid file instead of individual lines. So this process involves going to the MCA spectra menu, go to HDF5 right compression and select GSIP9. Go to the MCA spectra menu again and select Construct Express 3 HDFs. Express 3 is the detection electronics that we use at the beamline. Select that, navigate to the uncompressed or unzipped file, select one of these files, it doesn't matter which one, and select Open. You then get a dialog box asking if this was a bidirectional scan. Up until very recently, and certainly for beamlines 2.3, 14.3, your data will not have been a bidirectional scan. More recent updates to the beamline software make this a much higher probability. But if your data is older than 2020, then select No. You'll now see that SMAC has a little message down at the bottom here saying reading HDF files. Now, this can take a little while depending on how big your map is. I already did this with this file, which is quite large, and it probably took a good 20 or 30 minutes. So regardless, it's good to go get a coffee at this point. We're going to skip ahead in this video to the process being finished. After a little while, SMAC should read with the ready message at the bottom of the main window. That means the process is completed. You can also read the progress of this process by looking in the command prompt if you're working with Windows. So to find the file that we just collected, go to the directory that you're working from. In this case, I'm working from my T drive. And now, in that folder where there are all the individual map lines in the HDF5s, it should now have created a new file, which is your file name, but instead of a number at the end, it should say _MCA. At this point, we're done with all the individual map lines. So you can actually delete these files to save the space. As you can see, with this particular map file, each line is 20 megabytes in size. Don't worry, you'll still have the original compressed version of the file, but it's fine to delete these right now and save yourself a bit of space, because once you've done this process once, you never have to do it again, and you'll always work with this MCA file. So now we're going to load this MCA file into SMAC. We're going to click MCA Spectra menu and then click Define MCA. That simply means we're going to define the MCA file that belongs to this map. I'm going to scroll all the way down, select the MCA file. It's now read in. The next thing that we've got to do is select the MCA spectrum menu again, and then do View MCA. This now selects the MCA data as an option when we click on the map here, which I'll show you how to do now. Double click on a pixel or any location on your map, and you'll get two new windows. You'll get the standard line profile plots in the X and Y across the pixel that you selected. But now you'll get a new MCA spectrum view, and you'll see here we have the XRF spectrum that was collected at that pixel location, with the energy across the x-axis and the number of counts along the y-axis. You'll notice that this spectrum is very noisy, and that's because this is the spectrum in one pixel that was collected over your dwell time of your map, which could be on the order of a few milliseconds, so the statistics are probably quite low. We can improve on that by selecting a region of pixels. So on the map, right-click, and under mask type, you can select what type of shape that you want to mask. Freeform allows you to draw any polygon you like, so you can draw around particularly weird shape features, a circle and a rectangle. I'm going to select rectangle, and to draw a mask, you're going to hold down the Shift key, click anywhere you like to start in one corner of the region you're interested in, and then go down and click again to define the other corner. Keep holding the Shift key down and double click. You'll get a new pop-up window called ROI selection, which gives you the option of MCA, mask, MCA, and mask. Just selecting the mask will then temporarily mask out just the region you selected. We want to select MCA because we want to see the MCA over this region. So click on that and click OK. And depending on how many pixels you selected, it could take a few seconds. But now, this is the average spectra over the region we selected. And you can see the spectrum is much cleaner. The default is the standard linear view. But under the View menu, you can go to Trace Scale and change it to logarithmic. This is quite useful for finding much smaller peaks. So that's the basic process of getting your MCA data loaded into SMAC. Now, while being able to qualitatively assess the XRF spectrum at every pixel, or any pixel that you like, is somewhat useful, there are a couple of other things that we can do with this data. The first thing I'm going to go with is redefining bins. Let's say, for example, you made a bin too big in XMAP GUI when you were collecting your data, or you've realized that there was an element that you should have mapped and now are interested in, but you don't have that data in the original channel file. That's okay, because you can rebin using the XRF MCA data here. If we select under the MCA menu, rebin MCA to data, we get another little pop-up where you can then set the bin ranges. For example, I'm just going to put, even though we have iron, I'm going to put another bin over iron just to give you an example. So we can do 620 to 660, because the iron window is located at 6,400 EV. Remember, these numbers are a factor of 10 off. Now you see the MCA data is compressed here, so we're going to use the magnifying glass here to zoom in on just that region. And so you now see a little dark green bar has appeared over what is the iron fluorescence peak. Now say this, you can put any sort of range in here and use it to define new channels, new element channels. So let's just call this FE2 and click OK. Now this may take a little while because it's now integrating the entire map, but eventually we'll end up with a new channel in the main window. We scroll down to the bottom, we now see that that new channel has been added over here. The next thing we can do is somewhat more complex, and that's fitting the XRF spectrum. The advantage of fitting the XRF spectrum is that we can select the elements of the periodic table and the software will integrate all of the XRF emission peaks based on fundamental parameters. Once you've done a thorough fit, you'll then get a new set of channels saved into the main window, which should be far more accurate than the standard binning. This is particularly useful if you have overlapping peaks. For example, if you had a window over manganese and iron, you can see that if we had two bins across here, actually a portion of the photons belonging to manganese could actually be being contributed from iron. Doing the fitting process actually does a proper integration based off the known parameters of the manganese K alpha emission peak or any other emission peak, and therefore does a better job of displaying the true distributions of these elements. The main thing about doing the fitting is making sure that you select the right elements that are in your sample. This is not a one-click and go button. You have to tell the software what elements are in there and use your own intuition about what's present and what's not present. We simply can't just select the entire periodic table and ask the software to work it out for us. So, how do we do that? So what we're going to do is actually click View Config. It takes a couple of seconds to load up this new window. We get a new window called the MCA parameter configuration. And we're greeted with an interactive periodic table. This is where we select the elements that we want to fit in the XRF spectrum. It's already preloaded with some common elements. So if I go back to the main window and I hit Fit Current, it's going to try and do a fit of the spectrum based on the elements we've selected. You see the spectrum's changed to produce a green overlay over our real data. Now you can see some of the elements have already been picked out quite cleanly already, such as calcium, iron, and a few others. But not all of the peaks are being fitted. This is quite a rough fit, and there are some peaks that are missing. So we're going to try and, the basic principle here is we're going to try and make this green line sit nice and tight over your real data. And we're going to do that as an example here. One of the best things to do here is to go into the parameters first, and we're going to unfix all these parameters that we see here. The other thing that we can do is we probably want to trim down the XRF spectrum a little bit because we get a bit of noise and degradation of the signal, anything below about 1500 EV and anything above the beam energy. Now you see these fitting regions here, the minimum bin and the maximum bin, represent the upper and lower limits here. Now I know my map was collected at 13,500 EV, but it's currently trimmed to 1200 EV. So I'm just going to change this to 1400 and do fit again, or fit current. You'll now see it's extended a little bit, and what you actually see here, this is the elastic scatter of the incident beam. Let's just extend it out a little further to 1500. Do fit current. You can see we now see at 1500 we get this noisy tail dropping off. So let's pull this back to 1450. That's pretty reasonable. And also let's try and trim this to 150 or 1500. That's a bit better. We've gotten rid of some of that potential noise off of each end of the spectrum. So now what we're going to do is go back to the peaks, and we're going to try and make this green line fit better. Now I'm doing this live now. I haven't done this myself. So this is a live attempt at trying to fit this spectrum. Some of these elements you're going to be confident are in your sample, so go ahead and select those. Others you may not be aware of. But don't go nuts trying to make an XRF spectrum fit by putting in some really weird elements that are very unlikely. There's a lot of sample intuition here. Well, I don't think there's any lead in my sample. So first of all, I'm going to clear this preloaded lead M line. And I'm going to hit the clear selected button. To select an element, to add it to the fit, you're going to click on the element icon, and then you're going to select which emission line you want. In this case, I want to check the silicon K line, and it's now added here. Let's see if that made any difference. I think it tidied up this end of the spectrum a little better. What might we have over here? If we hover the cursor over the MCA spectrum here, we also see that on the X reading, we get a value across the X region. So this looks like it's nickel. That's about 747. So I'm going to add the nickel in there. Nickel K. Fit current. Getting better. You have to be careful a little bit with nickel, because if you have a lot of calcium, you can end up with double calcium fluorescence, which sits right on the nickel peak. What's this one over here? This looks like it could be, looks very close to arsenic. We already have arsenic. So let's actually try putting the lead line back in. I'm going to put the lead L in, because that's what I know is excitable by the beam. Well, that didn't fix that, but it potentially resolves some other peaks. I'm going to put in some other common elements too now. So vanadium K, titanium K, phosphorus. There should also be a little bit of cobalt in here, potentially some bromine. And that's the basic process. Another useful feature is that if you select the element in your active peaks here, you actually get the emission lines displayed on the MCA spectrum view to help confirm those peaks. Now, this isn't the best fit in the world, but for the purposes of this video and to show you how to go about doing this process, we're just going to go ahead and go on to the next step. We now want to fit the data. So forewarned, this can be a somewhat lengthy process. Sam has recently installed a faster map fitting function, which took the process down from what seemed to be infinity sometimes down to maybe many tens of minutes, maybe less depending on the area you decide to fit. So if I was to select Fit All MCA, the program will try and go through and fit every single spectrum in this map, in every single pixel, which would take a really long time because there's hundreds of thousands of pixels in it. If not, maybe might be a megapixel image. If you want to do it over your whole map, that's fine, but I recommend setting that going and waiting overnight for it to finish. The other option is that you can fit a smaller area, and that's where the Fit Zoom MCA comes in. Again, for the purposes of this video, we're going to do a really small area just to show you the process. So if we just use the normal zoom function and draw a pretty small area, like so, we're now going to fit this area using these fit parameters. But before we go into that, we're going to save this parameter file. We're going to go over here and do save config, and then just call this anything that you like. Now this defaults to a folder within SMAC called the PyMCA configs. You can put it anywhere, but this is the default one, and you'll be navigating outside this folder every time you want to do it. So I'm just going to call this test config. Now, if anything happens during this process, or you want to go away and come back to the data later, all you have to do is load config, and it will bring in all the parameters, including all the elements we just selected. So let's do the Fit Zoom MCA. On the Windows machine with the command prompt, you can actually watch this process as it happens. So because I picked such a tiny area, it's actually done it really quickly. For bigger areas, it will take a little bit longer. But what you can see now is that the main window data channels has been populated with a series of new data channels. And these channels are labeled after the element and the emission line that you selected in your periodic table. We can now select each of these and see what the map data looks like. And we can compare it to the original fit data. Let's pick an element that might have some overlap. This is the manganese K of the fitted. And this is the manganese of the regular bin data. And you can see if we select between the regular iron and the regular manganese, it would appear that manganese is pretty much closely correlated to iron. Intensities are slightly different, but that's because we have a bin over the manganese peak, which is much less intense. And the contribution from the iron photons is also less intense here too. If we now compare the iron and the manganese peaks from the fitted data, the iron doesn't look much different, but the manganese looks quite a bit different. Let's compare again between the manganese K fitted data and the manganese regular. You see the contrast is much less significant in the fitted manganese data, and that's likely because, and this is most likely a better representation of the manganese distribution of this sample. Whereas the manganese distribution here is partially reflecting the iron distribution as well. So this is a good process to do if you have significant contributions of different elements with closely packed emission peaks. At this point, save your data. You can overwrite it or you can call it something else. And now you'll be able to revisit all these data channels in the future. That's it for basic MCA fitting.